Hello and welcome to the Algebra 2 Test 6 study guide for logarithms. So if you're here, I'm guessing you didn't do too well on the test the first time around and you're here to do better. So I think by watching this video, doing some practice problems, I think you'll feel a lot better about logarithms and what we're doing with these types of exponential equations than what you did before. So we'll go through the 10 problems that are on this study guide that exactly match up with the problems that are on the test. So after we go through the study guide here, I think that you'll feel a lot better about taking the test. So first of all, first things first, let's just make sure you got your name on your paper. So let's go ahead and write name. Go ahead and write your name at the top. And if you're coming from a different teacher other than myself, if you'll just write your teacher's name. Your teacher's name. Alright, well, let's go ahead and get started on this. And again, just kind of set the stage for you here a little bit. You'll notice there's 3 columns, left, middle, right. So the column on the left side, that will be me kind of explaining it to you, tell you how to do it. And then the column in the middle and the column on the right side will be for you to actually try and practice. So similar to training wheels on a bike, the idea is that you have the training wheels on there in the beginning, but eventually you take the training wheels off, you try to start doing it on your own. That's the idea of what we'll do in this video. Is left side is me showing you how to do it, and then progressively we take off the training wheels and we have you do it on your own. So that's the idea there. So if you just copy what I write down, you're not going to get as much out of it. It's not going to do you as much good. So what will do you the most good is try to do as much as possible on your own. Alright, what's a logarithm anyway? Well, logarithms are just another way to write exponents. What we do, and how this is different, and this is the first time you're seeing this in Algebra 2, is that in Algebra 1, when you solved an equation, x, or y, or whatever the variable was never an exponent. So you notice that in these equations, the variable is an exponent. So that's what makes it an exponential equation, is because the exponent is a variable. Now, sometimes it's real easy. You can just kind of look at an exponential equation and know what the answer would be. So for instance, this one says 2 to the what power makes 16. Well, 2 times 2, 4, times another 2, 8, times another 2, 16. Right, so that would be 4 times. Or for something like 3 to the what power makes 27. What number times itself 3 times makes 27? Well, 3 times 3 is 9, times another 3, which would be 27. So, x would equal 3. But then what we encounter, and what we'll see in this study guide and what we see with logarithms in Algebra 2, is that sometimes it's not as easy as what we just said over here. So for instance, this says 4 to the what power makes 30. Well, if you think about the powers of 4, 4 to the first power is 4, 4 squared is 16, and then 4 cubed is 64. So the powers of 4 actually don't stop off at 30. It skips from 16 to 64. Now there is a number that goes in there, a value for x. It's just not a whole number. So because 30 is somewhere between 16 and 64, then what this value would be somewhere between 2 and 3. And being between 2 and 3, that just means that it's going to be a decimal. Well, to get that value, that's something that we're going to need a calculator for, and hence, that's where logarithms come into play. So that's just kind of give you a little bit of background on what we're going to be doing in this section with logarithms. Alright, well, let's go ahead and take a look at the first problem. So it says, solve log base 2 of x equals negative 4. And by the way, that's how we say it. So we say the word log, and then the number down here, that is the base. So we'd say log base 2. And then there'll be some term here, either a variable or a number. So we'd say log base 2 of the term that's here, which in this case is x, and then equals negative 4. Well, so the thing is that I just mentioned that there are occasions where we need a calculator to solve these types of problems. But we don't want to assume from the very beginning that we need a calculator, because maybe, just maybe, it's like the ones that were over here, where we could just kind of figure it out by looking at it, where we didn't actually need a calculator. Well, if that's the case, then we want to solve it on our own without needing to use a calculator. It's not to say that the calculator is kind of a last resort, but we check to see if we can solve it mentally on our own first. If you take a look at the diagram that I have over here on the right side, so there's two different forms, logarithmic form and exponential form. And so you'll notice that this problem is written in logarithmic form, and obviously it's easy to pick out its logarithmic form, well, because it's got the word log in it, right? So that's logarithmic form. So what we want to do is we want to rewrite this in a way that we're used to seeing. We're used to seeing things in exponential form, where you have some base, there's an exponent, and then that's equal to, you know, some number, right? There's no word log. So what we're going to do is we're going to rewrite this, and what ends up happening is that the base, represented by the letter B, you'll notice that it's always on the left side. So the base stays the same, and then it's the two other numbers that are switching places, or two other terms. So this one's coming over here. And again, all we're doing here is we're just rewriting this in a form that we're used to seeing, or that we're more comfortable with seeing. And then this is going to come over here. The base stays the same, so the base in this case would be 2. And then the negative 4 is going to come over. So that would be negative 4 and equal to x. And if you want to, you know, a lot of times we're used to seeing the x on the left side, so we could rewrite that as x equals 2 to the negative 4th. And so now what we want to do is we want to say, okay, well, what is 2 to the negative 4th? Well, so we can work with this. We don't need a calculator. So again, just think of it this way. They gave it to us in a way that's written in a little bit different form, like we're going to use a calculator or something like that. It's written in logarithmic form. We're just rewriting it. All right, well, what does 2 to the negative 4th mean? Well, this requires us to kind of take a step back and think about what does a negative exponent even mean to begin with. Well, so if you think about like what 2 to the positive 4 is, you know, 2 to the positive 4 means 2, 4, 8, 16, right? So 2 to the positive 4 is 16. And then 2 cubed, which is 2 times 2 times 2, which would be 8. 2 squared, which is 4. 2 to the first, which is 2. And then we get to 2 to the 0, and it's like, well, what would 2 to the 0 be? Well, look at what's happening here. From 16 to 8 to 4 to 2, those numbers are being divided by 2. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. So what do you think is going to go right here? Well, 2 divided by 2 would be 1. And then notice what happens if I keep counting down. Look at the exponents. They went from 4 to 3 to 2 to 1 to 0. Well, let's keep counting down. So we would dip below and get into the negative territory, and we'd be at 2 to the negative 1. Well, if the pattern on the right side was to divide each term by 2, let's keep dividing by 2. So 1 divided by 2 would be 1/2. Let's keep going on the pattern. 1/2 divided by 2, half of a half is a fourth. Half of a fourth is an eighth. And half of an eighth would be a 16th. So what you notice what happens here is that the second that we dropped into the negative territory right there, you notice that the numbers became fractions. So if 2 to the positive 4 is 16, you notice that 2 to the negative 4 was just 1 over 16. So what happens with negative exponents, it doesn't turn the number into a negative number. What it turns it into is it turns it into a fraction. Now, the way that we could rewrite this, 2 to the negative 4th, is that we just said that it turns it into a fraction. So that would be 1 over 2 to the positive 4. And 2 to the 4th, as we've just said, would be 16. So the answer there would be 1 over 16. So the key idea coming out of this is that negative exponents, make a little note here, negative exponents, I might run out of room there. I should rewrite that. So negative exponents make numbers fractions. Make numbers fractions. So that's what it turns into, right? So and we kind of proved. There's actually also something else we proved, which is that anything to the 0 power is equal to 1. So that's actually something else that we proved by just writing it out in that way. All right, so that's the first one. So you go ahead and try number 1 in the middle, and again, the way that this will work, I'll show you the first one. You try the middle, the one on the right. Again, do as much as this on your own as you can, and then we'll check the answers here in a second. Alright, so you should have had an opportunity to have number 1 in the middle. The answer for number 1 in the middle would be x equals... actually, let me back that up. Oh, there we are. Number 1 in the middle would be x equals 1 over 25. I think what you just saw was number 1 on the right side would be 1 over 27. Now, for number 1 in the middle, if you did get 1 over 25, then you can go ahead and move along, try number 1 on the right side. If you didn't get 1 over 25, then I'll kind of show you real quickly where we got that from. So again, rewriting in exponential form, so the base always stays the same, the number that's on the far left over there. It's just the other two numbers that are switching places. Or in this case, we have a variable. So the base stays the same, which is 5. And that idea of the base staying the same, that's the deal with this thing Benny and Ben. Benny and Ben both start with the letter B, meaning that the base is always the first thing that's on the far left. And then the difference between Benny and Ben is just that the other two terms have switched places. So 5 to the negative 2 equals x. And again, just personal preference, kind of like to flip this around. Alright, so you got a negative exponent. We just said that negative exponents make numbers fractions. So 5 to the negative 2 would be 1 over 5 to the positive 2. And actually, when we looked at rational expressions, we've already looked at negative exponents. We also said turn that frown upside down. And what we meant by turn that frown upside down is that if you had a negative exponent, turn that frown, negative, upside down, reciprocal. And when you turn a frown upside down, you have a smile, right? You have a positive. So that's the idea of turn the frown upside down. And then 1 over 5 squared, which would be 1 over 25. Alright, so go ahead and try number 1 on the right side. And if you've already got that, then let's go ahead and check what the answer was. And I think a second ago we already showed that. But yeah, you should have got x equals 1 over 27. Alright, so if you didn't get that, try to figure it out, and if not, ask for some help. So let's look at number 2. So number 2 is really a very similar problem to the last one. You'll notice that there's a fraction in it. That's okay, don't be afraid. The first thing that we're going to do on this is we're going to rewrite it in exponential form, meaning we're going to rewrite it without the log. So again, base stays the same. It's the other two terms that are going to switch places. And so what this would end up being is it would be 64. This down a little bit. It would be 64, and then that 2/3 would actually be the exponent. So the exponent's actually a fraction. And then we get equals x. Again, I'm just going to flip it around. So I'm going to say x equals 64 to the 2/3. Alright, so in the last one we said that a negative exponent rather, turns the number into a fraction. And then it's like, well, what if the exponent itself is a fraction? What does that mean? Well, there's a couple different ways that we can look at this. But basically, one way that you think of this is that the fraction is kind of telling you two different things because there's two numbers up here. Well, we can only kind of do one thing at a time. So the way that we can rewrite this is that we can take whatever the numerator is, we can push that off to the outside and then leave the denominator as a fraction. Right? And again, the reason why I'm doing this is because I have two numbers up there as an exponent, right? Because I've got a 2 and a 3. And so what I'm trying to do is I'm trying to just do one thing at a time. So I'm kind of separating this. And so what I can do is I can push the numerator out to the outside and then just worry about this part of it, get that number, and then square whatever that would be. And it's not magic. I didn't make that up. You know that your rules of exponents is that if you have an exponent on the outside, that you can distribute it to whatever's on the inside. So 2 times 1 would give you 2. So that is a legal move. I just didn't make that up. Now, what does 64 to the 1/3 mean? Well, let me kind of go to the side and do a little scratch work here. What 64 to the 1/3 means is this is just another way to write it. This is written in exponential form. We would rewrite this in radical form. The number on the inside, the number on the numerator goes on the inside. The number on the outside, denominator goes on the outside. So this is really just another way of saying what is the cube root of 64. Because if you think about what an exponent means, if it said 64 to the third power, that would mean 64 times 64 times 64, making it larger. 64 to the 1/3, less than 1, what that's doing is actually making it smaller. So it's another way of saying what number times itself 3 times would give you 64. Well, that number would be 4. So what this means for us here is that 64 to the 1/3 would be 4, and then we still have that 2 hanging out front, so 4 squared, which would be 16. And I could have rewritten this from the very beginning. I could have rewritten this in radical form, but what I would have ended up doing there is that I would have squared 64 first, and then take the cube root of that. Well, 64 squared is some really large number. So what I did instead is I took the cube root first and then squared it, right, keeping the numbers a little bit easier to work with. All right, so go ahead and pause now. Try number 2 in the middle. All right, so let's see what you got for number 2 in the middle. So for number 2 in the middle, you should have got x equals 4. If you got that, great. Give yourself a pat on the back. If you didn't get that, well, then let me show you how we would get x equals 4. If you did get it, go ahead and pause. Try number 3 on the right, or I'm sorry, number 2 on the right. If not, let's take a look at what happened there. So again, it's written in logarithmic form with all of these. What we're trying to do is we're trying to rewrite them in the way that we're used to seeing them, which is in exponential form. Not that we called it that, by the way. You know, when you do something like, I don't know, like 3 squared equals 9, which you never called it exponential form, but that's what it is, right? So we're just rewriting it in a way that we're more familiar with. Because maybe we don't have to use a calculator, right? So that's what we're checking to see. We're checking to see if we can actually solve this without needing to use a calculator first. All right, so let's rewrite this. You got 32 to the 2/5 equals x. Again, I'm just going to rewrite that as 32, x equals 32 to the 2/5. And as we said a second ago in the last problem, is that this exponent, because there's 2 numbers up there, it's kind of telling me to do 2 different things. It's telling me to take the 5th root of something, and then it's also telling me to take the square of something. Well, I'm trying to keep this simple, and I'm trying to just do one thing at a time. So what I'm going to do is I'm going to split this apart and kind of break it up into 2 different steps. So what I'm going to do is I'm going to take the numerator and put that to the outside, which is 2. And then if you move the numerator to the outside, what would be left would be 1/5. Right? And you might wonder where'd the 1 come from. Well, if I did 2 times 1, that would give you 2, so that would have to be a 1 there. Now, what does 32 to the 1/5 mean? Well, what 32 to the 1/5 mean, it's another way of saying, just doing a little scratch work up here, it's another way of saying, what is the 5th root of 32? What does that mean? Well, what the 5th root of 32 means is it means what number times itself 5 times would give you 32. Well, 2, 4, 8, 16, 32. You can't see me right now, but I'm counting on my fingers how many times, if I multiply by 2, how many times it takes me to get to 32. So that would be 5 times, right, counting by 2s. So what that means is 32 to the 1/5 would be 2, and then 2 squared would be 4. So again, we're trying to simplify things by just doing one thing at a time and breaking that off into a couple different pieces. All right, so go ahead and pause now. Try number 3 on the number 2. I keep saying 3. Number 2 on the right side. All right, so let's see what you got there. So you got x equals 9, right? So make sure you got that. If not, try to figure it out. If not, we'll go ahead and move on. All right, so this says simplify log 4 of 64, And then you'll notice what's different here is that it doesn't say equals and then, who knows what. So this is actually written in kind of a shorthand way. And what this is really saying is it's saying 4 to the what power makes 64. Now what I'll do here is I'll go ahead and write this in a, similar to what we were looking at. Because if you go back to the last one, you'll notice that everything had an equal sign on there. So we'll write that what you're used to seeing. So equals, and I just put x because I don't know what it's equal to, right? So that's what we use a variable for, is some sort of unknown number. Same drill. Let's rewrite this in exponential form. Base stays the same. It's the other two terms that are switching places. So this says 4 to the x equals 64. Well, again, this is another way of saying, if I were to translate this, this is saying 4 to the what power makes 64. Well, so if I think about the powers of 4, I think we already wrote that out on another one of them, right? 4 to the first power is 4. 4 squared is 16. 4 cubed is 64. So what that means is that 4 to the third power is 64. So x would equal 3. Right, now all I did in this last step is that I rewrote them with like bases, and that's going to come up here in a minute. And there's a property that we'll discuss a little bit further that says that if the bases are the same, then whatever is on the top line where the exponents are is the same as well. So you get x equals 3. Alright, so pause now and try number 3 in the middle. So for number 3 in the middle, you should have got x equals 3. If you got that, then go ahead and pause and try number 3 on the right side. If you didn't, then let's kind of hang on for the explanation there. Well, first of all, whoop, didn't mean to move that. Well, maybe we will. The kind of is in the way there, because what I want to put on there is I want to throw the equals x on the end of there. And then I want to rewrite in exponential form. And so what I come up with there is I come up with 3 to the what power makes 27. Well, if I think about the powers of 3, 3 to the first power is 3, 3 squared is 9, and then 3 cubed, which would be 27. Now, what I'm writing out over there, by the way, you don't have to write that out every time. That's just me kind of showing you the thought process of how you'd go about thinking what the answer would be. So, for instance, in here, we get x equals 3. All right, so go ahead and pause. Try number 3 on the right side. All right, so let's see what you got for number 3 on the right side. Number 3 on the right side, you got x equals 5. And, again, what that's saying is it's saying 2 to the what power makes 32. So if you think about the powers of 2, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth is 32. So that's why the answer there would be 5. Alright, so let's move along. Let's take a look at number 4. Again, looks very similar. Only difference here is there's a fraction in it. That's okay. We're not scared. We can handle that stuff. So first thing I want to do is I want to throw the equals x on the end of it, and then I want to rewrite it in exponential form. So let's throw this x over. Let's take 1 over 81, put that over to the other side, and then again I'm just rewriting this in a way that looks a little more familiar to me. Alright, so what this says, it says 3 to the what power makes 1 over 81. Well, if I think about the powers of 3, and I say, well, 3 to the first is 3, 3 squared is 9, 3 cubed is 27, and then 3 to the fourth, which would be 81. But here's the deal. I'm not looking for 3 to the what power makes 81. I'm looking for 3 to the what power makes 1 over 81. Well, remember, we just mentioned a moment ago that anything to the 0 power would be equal to 1. And then what happens is when you drop down into the negatives, that's where it's really the same number. It's just that it's a fraction. So 3 to the positive 1 is 3. 3 to the negative 1 would be 1 over 3. So what we could say is that if 3 to the positive 4 is 81, then what that means is that 3 to the negative 4 would be 1 over 81. Now, how I could rewrite this, by the way, is I can rewrite this as, so I already know the answer is x equals negative 4. But what I can do here is I can rewrite this as 1 over 3 to the positive 4. And then we said turn the front upside down a moment ago when we turned a negative exponent into a fraction. Well, we can go the opposite direction with that, which means that we can take this frown, or smile rather, turn it back into a frown, meaning I can take that positive exponent and put it back into a negative exponent. And then so x equals negative 4. Right, but not that you wouldn't have to go through each one of those steps that I showed there. I think if you got here, it'd be good to recognize, oh, it's 1 over 81, so that means it'd be 3 to the negative 4. All right, so go ahead and pause and try number 4 on the middle. All right, well, let's check what you got with number 4 in the middle. Should have got x equals negative 5. If you got that, go ahead and pause, try number 4 on the right side. If you didn't, again, hang on for the explanation here. As always, start by putting the equals x on there, and then we're going to rewrite in exponential form. And basically, exponential form just means that we're rewriting it without the log on there, because we're not used to seeing something that says log. So 2 to the x equals 1 over 32. Well, now again, if I talk about the powers of 2, and again, we don't have to write this out every time, but I'm really trying to make this point here so that you get the visual of what's happening. 2 cubed equals 8. And if I kept going with that, probably should have started a little lower here. Let me scoot that down a little bit. So let's try 2 to the 4th, which is 16. And then 2 to the 5th would be 32. Well, hopefully, and the reason why I keep drawing this out is that I want you to be able to get to the point where it becomes rather automatic that you notice that anything that has a negative exponent, all that means is that the answer would be a fraction. So if 2 to the positive 5 is 32, and we're looking for 2 to the what power makes 1 over 32, well, skip down, 2 to the negative 5th would be 1 over 32. So our answer there would be x equals negative 5. Yep, so x equals negative 5. All right, so try number 4 on the right side. All right, checking to see what you got with number 4 on the right side. Oh, wow. Wait, hold on. What happened here? Oh, okay. Just went too fast. Sorry. All right, number 4. Sorry, it's 8:18 at night, so I get a little loopy here. So yeah, number 4 on the right side there. So x equals negative 2. And again, what this is saying is it's saying 4 to the what power makes 1 over 16. Well, 4 to the positive 2 makes 16. So 4 to the negative 2 is what makes 1 over 16. All right, so let's take a look at number 5 here. So this says 3 to the what power makes 3x minus 5 equal to 81. All right. Well, so this looks a little bit different. First of all, you notice it doesn't say the word log on it or anything like that. It's actually already written in exponential form. Now, what we can do with this, and if you'll notice over here on the right side, what this says is that if b to the x, and b just represents any base, is equal to b to the y. So basically, if the bases match, then x equals y. And what that's saying is that it's saying that if the bases are the same, and you're trying to figure out what's going on with the exponents, then you can drop off the bases and just focus on the exponents. Now, if you look at it as it's written, the bases are not the same. 3 and 81 don't match. But what you do is you look at the bigger number and you say, all right, well, what can I do to the bigger number to rewrite it so that it looks like the smaller number? So if you think about the powers of 81, and again, I'm not going to write them out this time, but hopefully some of the stuff becomes a little more automatic for you. 3 to the first is 3, 9, 27, 81. So that would be 3 to the 4th. So 3, actually I want to go different color on this one. So let's say 3 to the 3x minus 5, 3x minus 5, equals, and now we just said that 81 can be rewritten as 3 to the 4th. Right? And again, just so you make sure you see where I'm getting that from, 3 to the 4th, because 3 to the 1st is 3. 3 squared is 9. 3 cubed is 27. And 3 to the 4th is 81. And then so what this property says is that once you have like bases, then you can just focus on that part of it, which means the bases kind of drop off. And you can't see this, but I'm taking my hands and I'm covering up the 3's to show you that I'm just focusing on the highlighted part of it, which is this part right here. 3 to the x minus 5 equals 4. Well, then from there, what I can do is I can solve... What the hell's happening here? Add 5. There we go. So I can solve that equation by adding 5 to both sides, and so I get x equals 9. Sorry, not x equals 9, x equals 3. 3x equals 9. Right, so the whole idea there is that we wanted to, the big idea with this one is that we wanted to rewrite with like bases. Because once we could do that, then we could focus on where all the action is. All the action, where x is, it's up there. Which again, that's what makes this different from Algebra 1, is that you never saw an equation that had x as an exponent, right? The variable's never been an exponent for us. So that's what makes that look a little different. Alright, so go ahead and pause now and try number 5 on the middle column. Let's check what you got with number 5 in the middle. So you got 10 over 9. I apologize. I don't know if I necessarily meant the answer for this to be a fraction. It's not to say that you couldn't get a fraction, but I think I was trying to keep things clean and keep them to whole numbers. But nevertheless, for this particular one, the answer actually is a fraction. So, you know, if you got that, thought you made a mistake, you didn't make a mistake. That's what it is. So if you got that, then go ahead and pause. Try number 5 on the right side, and again, we'll try to figure this out together here if you didn't get it. So let's rewrite it. And by the way, I probably should have mentioned this sooner, is that, you know, as we're doing this, you know, let's say you didn't get this one right, or you weren't quite sure about this one. You know, but maybe the second that you figure it out, then don't just keep watching me do it. You pause it and you try to finish this on your own, right? So again, trying to do as much of this as possible on your own. Alright, so what we said is we want to rewrite these things with like bases. And we have a little color scheme going. So the bases we were doing in blue here. And the exponent there, 9x minus 6. And then we wanted to rewrite 256 as a power of 4. So if you think about the powers of 4, let's kind of come over here. 4 to the first is 4. 4 squared is 16. 4 cubed is 64. And then 4 to the fourth is 256. Now, how do I know that? Well, I've done these problems so many times, you just start to kind of remember some of them. But you know, if you're not sure about that, there's nothing wrong with doing a little scratch work, right? Like 64 times 4, 256, right? So that's, but I think you see these same numbers keep popping up, so I think eventually you'll start to recognize them. So we can rewrite this. We just kind of showed that 4 to the fourth is 256. So we can rewrite 256 as 4 to the fourth power. And as we said, what this property over here lets us do, when we say that if x, or if b to the x equals b to the y, then x equals y, again, all that's saying is that if these numbers match, then you can kind of think of them as that they drop off. I don't want to say they cancel, because that's not necessarily mathematically correct, but the idea is that we're just focusing on that top part where x is. Right? So we're just trying to get x by itself. So we're just focusing on the part that has the x. 9x minus 6 equals 4. So let's add 6 to both sides, and you get 9x equals 10. So you get x equals 10 over 9. Alright, so go ahead and pause now. Try number 5 on the right side. Let's check out and see what you got for number 5. On the right side, should have got x equals 2. Alright, so if you didn't get that, try to figure out what happened there. If not, then we will move along. So we're passing the halfway mark here. So number 6, so we're flipping on over to the back side there. So this says simplify 5 to the x equals 28. Alright, so on the back side, this is where we start getting into, what if we can't do this mentally? What if we need a calculator? Right, so that's what these problems begin to address. Think about the powers of 5, by the way. 5 to the first is 5. 5 squared is 25. 5 cubed, 5 times 5 times 5, is 125. So what you'll notice is that the powers of 5s don't stop off at 28. It jumps from 25 to 125. Now I would suspect that x is somewhere between 2 and 3, probably a lot closer to 2, right, because 28 is pretty close to 25. So maybe it's 2.1, 2.0 something. But that's what a calculator would figure out for us. But what we have to be able to do is that I can't just, as it is, I just can't stick that into the calculator. So what I need to do is I need to rewrite this in a way that I would be able to type it into the calculator. Because I tried to do it on my own first, and it doesn't work out to be a whole number of answers. That's where we need a calculator. Well, so the first thing that happens is when you notice or you realize that you need a calculator, that's where we use logs. And what I do is that I'm putting log into the equation because I can't do it without a calculator. And what I do to one side, I do to the other side. So basically what happens here is that we turn the logs on. You write the word log on both sides of the equation. And what we're trying to do is we're trying to get x by itself. Well, what you'll notice is that I've put over here on the right-hand side several of the log properties that we're going to be looking at over the next several questions. And the third log property that I just highlighted, what that says is that if you have something that is an exponent, so you have the letter n, that it can be rewritten as a term that is no longer an exponent and that it's in front of the log. So what I'm going to do is I'm going to rewrite this. I'm going to pull this down over here. I'm going to rewrite that as x times log of 5 equals log of 28. And again, what we did there is we're trying to get x by itself, but I can't get x by itself if it's stuck up there in the tree, if it's stuck up there as an exponent. So all I'm doing is I'm bringing it down first to begin the process of getting it by itself. Now what this says x times log of 5. We know the opposite of multiplication is division. So we would divide both sides by log of 5. And then what would be left would be x equals log 28 divided by log of 5. Get that off of there. Now, as we've mentioned in class, for purposes of the CST, you're actually not allowed to use a calculator. So for purposes of the CST, your answer actually would stop right here. And this particular question on the test, what I'm actually looking for here is I'm looking for you to be able to prove how we can take something that needs to go into the calculator, how do you rewrite it so that it's ready to go into the calculator. Now, just for fun on this particular one, I'll show you. We said that 28's in between 25 and 125, so our answer is probably between 2 and 3. So on this one, I'll do log 28 divided by log 5. And again, for the test, you don't need to do this. I'm just showing you how it all works out. And so we get 2.07, which is what we predicted. It would be pretty close to 2. But again, I'm just showing you that. For my answer here for number 6, though, I'm going to leave it. Alright, so go ahead and pause now and try number 6 in the middle. Alright, let's check out number 6 in the middle. Should have come up with log 40 divided by log 4. And again, that's how we're leaving our answer. The last questions on the test, that's where we're actually going to the calculator. Again, this is how would I get it set up before I get it into the calculator. So if you got that, great. Go ahead and pause. Try number 6 on the right side. And if not, then again, let's kind of walk through it. So again, 4 to the what power makes 40? Well, there's not a whole number. Again, 4 to the first is 4, 4 squared is 16, and 4 cubed is 64. So the powers of 4, it skips over 40. It jumps from 16 to 64, so it doesn't stop off at 40. So again, what that means is that that number, whatever x is equal to, it's not a whole number, it's a decimal. It's somewhere between 2 and 3. So I would need a calculator for that. So the second that I realize, oh, I need a calculator, that's where the logs come in. So that's where we actually write the word log. And it's this idea of that what you do to one side, you do to the other. So we have to write it to both sides. And then we're trying to get x by itself, because we're trying to get this set up, because as it is, I can't type it into the calculator as it is. So I need to rewrite this. And as we mentioned, there's a log property that says is that if you have something that's up there as an exponent, that what you can do is you can rewrite it. Instead of the exponent being on the inside, as you see right there, it can be rewritten with the exponent or with the number out front. So we're just trying to get x down from up there and down here. Now, so we end up with x times log of 4 equals log of 40. And then when we divide both sides by 4, we get x equals log of 40. And again, a second ago we made the prediction that this answer would be somewhere between 2 and 3, because 40 is in between 16 and 64. And again, just to kind of prove that real quick, let's clear out the other one, is that if I did log 40 divided by log 4, I end up with 2.66. And so again, that just shows you is that what I've done is I've now rewritten it in a way that I can put it into the calculator. Alright, so go ahead and pause now. Try number 6 on the right side. Alright, so for number 6 on the right side, you should have got x equals log of 12 divided by log of 2. Alright, so let's move along here. Let's check out number 7. So getting towards the end here, thanks for hanging in there. You're doing the right thing by being here, by listening to this video, and by redoing your test, and being an active participant, and doing what you can do to make your grade better. Alright, so this is an example of a logarithmic equation. Why is it an equation? Well, it's got an equal sign in it. Why is it a logarithmic equation? Well, because it's got logs in it, right? So it's kind of self-explanatory to a certain degree. So just like you solve equations, you know, if you solve an equation, you don't need to write this down, right? But let's say I had 5x plus 2x equals 14, right? I would want to combine my x's before I could actually continue to solve that equation. So it's kind of the same idea here, is that I've got logs, and I want to combine those logs. Now again, there's some rules that tell me how I can combine things. And the first thing that you might notice is you see there's a 3 that's out front. Well, you notice on the last one, we took the x as an exponent and we threw it out front. But what we're trying to do here is we're actually trying to solve, so we're actually trying to kind of compact things or kind of put things together. So we're going to use this same log property, but we're going to use the part of it that says that if you have something that's out front and you try to clean it up and you're trying to put everything back together, that you put it back as an exponent. So what would happen is that 3 would come back as an exponent. So what I would have is I would have x cubed, and actually that would be log base 7 of x cubed minus log base 7 of 2 equals log base 7 of 32. Now, so just like I said a moment ago, you're trying to combine x's, you combine like terms. In this case, we're trying to combine like logs. And then there's another log property that tells us how we can go about combining like logs, which is that if 2 logs are being subtracted, which in this case they are, right, because you see the minus sign right there. So if 2 logs are being subtracted, what this says, if you want to put them back together, you can put two logs back together as one log, but what you got to do is you have to divide the two terms amongst one another. So what that would look like is that I would have log base 7 of x cubed divided by 2. And maybe we'll kind of use the same color coding that we did over there. Right, so this would be x cubed, and this would be 2. Equals log base 7 of 32. So again, this log property says that if you have two logs that are being subtracted and you want to put them back together as one log, you can do that by turning it into division. So what this says is that subtraction outside of the log turns into division inside the log. Alright, and so just like on there was that other problem where we said, okay, when you rewrite it, and not to give you motion sickness here, but I'm going to flash back to number 5. Right, so we said that if you have like bases, then the bases drop off and you can just focus on the top line where the x is. Well, that's the same case here, which is that if you have like logs, think of it as that the logs drop off and you can focus on just the equation that's left over there. So for instance, what you could focus on is just x cubed over 2 equals to 32. So I'm just solving that part of it. Now, so I want to get x by itself. Well, the first problem here is that x is a part of a fraction. I don't want it to be a fraction. So this says x cubed divided by 2. Well, we always do the opposite in algebra to get rid of things. So the opposite of dividing by 2 would be to multiply by 2. So we're going to multiply both sides by 2, leaving us x cubed equals 64. Now we've already done this. This says what number cubed would give you 64. Well, it's 4 times 4 times 4, which would give you 64, so x would equal 4. Right, because 4 to the first is 4, 4 squared is 16, and 4 cubed is 64. Right, so it would be 4 to the third power. Alright, so go ahead and pause now. Try number 7 in the middle. Alright, so let's see what you have for number 7. There in the middle should have got x equals 6. And if you got that, great. Go ahead and pause now. If you didn't, let's take a look. Alright, so again, this is a logarithmic equation, so we're just trying to get x by itself, but I've got all these logs floating around. So again, the first thing that I'm going to do here is that this third log property that says that if you have something out in front of the log and you want to put it back inside the log, because we're just trying to clean things up here, then you can do that. So I would rewrite as log 4 base 4 of x squared minus log base 4 of 12 equals log base 4 of 3. Now I have another log property that says that if you want to put two logs back together, and that was not a highlighter. Let me switch that. Ah, there it is. There's the old highlighter. So what that says is if you have two logs that are being subtracted and you want to put them back together, you can do that. You have to divide the two things, right? So that's what this turns into. That subtraction turns into division. So x squared divided by 12, right? Because we're saying that's 12 right there, equals log base 4 of 3. Alright, so similar to the situation where if you have like bases, the bases drop off, same situation here, is that if you have like logs, the logs drop off, and then you can focus just on the equation, because again, we're just trying to get x by itself. So let's pull this out to the side. So you've got x squared over 12 is equal to 3. And then we're just trying to solve this particular equation here. We're trying to get x by itself. The problem is that x is a fraction. We don't want x to be a fraction. So we want to break this up. So how you break up any fraction, not just in this situation, but any situation, is that if you multiply by whatever's on the bottom, the denominator, then that will bust up that fraction, right? Because you can cancel those two things out. And then so what you're left with is x squared equals 36. And then what this is saying is it's saying what number squared would give you 36? Well, x would equal 6, right? Because 6 to the first power is 6. 6 squared is 36. Right, so you get x equals 6. All right, so go ahead and pause now. Try number 7 on the right side. All right, so let's see what you got for number 7 on the right side. Number 7 on the right side, you got x equals 5. All right, so moving along, almost there. Number 8. So this says approximate log 36, given that log of 2 and log of 3 is equal to some decimals. All right, so this is the kind of old school way before calculator way of looking at this. So what we're wanting to do is we're trying to figure out what log 36 is, but I don't know what log 36 is. I only know what log 2 and log 3 is. So what I'm having to do is I'm having to figure out how do I rewrite this number, 36, only using the two values they give me, 2 and 3. So what I'm going to do is I'm going to start off with log of 36, and I'm going to figure out how can I break this apart. And what I'm trying to do, the goal here, is I'm trying to break apart 36, where I get down only using 2's and 3's. Well, I don't know, think about what makes 36. 6 times 6, 9 times 4, 3 times 12. So I got some choices there. It doesn't really matter which one you choose, by the way, and I'll kind of show that in a second. I don't know. First thing comes to mind, maybe 6 times 6. Now, I don't know what log 6 is. I just know what 2's and 3's are. But I know that I can take log 6, which would be 2 times 3, and 6, which would also be 2 times 3. And I have another log property over here that says that if things are being multiplied and you want to pull them apart, you can do that by turning that into addition. So what this turns into, didn't want to use that. What this turns into is it turns into log base 10, and this is base 10 when you don't see it. Log base 2 plus log base 3 plus log base 2 plus log base 3. And now what I know is I know that log base 2, I can start making some substitutions here. Is that I know that log base 2 is 0.301, because they told me that. And then they told me that log base 3 is 0.477. So log base 3 is 0.477. So what I can do is I can start making those substitutions. 0.301 plus, we can do log 3, which is 0.477, and then we just want to add all those things up. And since we're using a calculator here, so we can use a calculator to tally all of that up. Let's clear out what we had. So we're just going to do 0.301 plus 0.477 plus 0.301 plus 0.477. Too many 7's. Sometimes that happens here. Let's take that out, and 1.556 is what we should have come up with there. So we end up with 1.556. So again, what you're trying to do is you're trying to take a number they throw at you. They throw 36 at you, and you're trying to figure out how can I rewrite that number only using the values they give me, which would be 2's and 3's. Right? So go ahead and pause now and try number 8 in the middle. Alright, so let's see what you got for number 8 in the middle. Number 8 in the middle should have got 1.255, and for number, and I'll just go ahead and show it to you, number 8 on the right side should get 1.079. So those are your two answers there for 8 in the middle and 8 on the right side. If you got both of those, great. Let's go ahead and move on to number 9. If you didn't, then let's go back and talk about number 8 in the middle. Again, that answer was 1.255. So log 18, they throw log 18 at me, and I'm trying to figure out how can I rewrite log 18 only using 2's and 3's. And it wouldn't always be 2's and 3's. It might be other numbers, right? So you just have to kind of go with what they give you. Well, so let's think about how you break apart 18. I can break apart 18 by saying 9 and 2. I can say 6 and 3. Again, it doesn't matter actually which one you pick, so just pick something, right? So 6 times 3. And then 6, which would be 2 times 3 times 3. And so now I can rewrite this because I can pull this apart. I can give each term its own log. So I can say log 2 plus log 3 plus log 3. And log 2, which would be 0.301. Alright, so there is 0.301. So where there's log 2, I'm going to replace that with 0.301 and then plus log 3. So let's see, log 3, which is 0.477. There's log 3, there's log 3. So plus 0.477, 0.477, and then let's add all that up. So if I added all those terms up, and again we'll get out the calculator here to take a look, 0.301 plus 0.477 plus, why is it throwing in that extra 7, plus 0.477, 1.255. 1.255. Alright, so go ahead and pause. Try number 8 on the right side. Alright, so number 8 on the right side should have got 1.079. I think we already mentioned that. Alright, so let's take a look at number 9. So number 9 says, now this is a word problem. Or actually I would argue it's a problem with words in it. But this is an example, so all this stuff you wonder, like logs, what's the point? So why does this even get used? Well, so this is an application problem. There's several things that are represented by exponential equations. One of those is being population, so it's an example of exponential growth. Something that starts off, if you look over at the graph here at the right, something that starts off really small and then takes off really fast. Another example we used in class was the idea of a YouTube video. Nobody heard of Gangnam Style 6 months ago, and then all of a sudden the guy's got 1 billion views. So the idea is something that starts off small and it takes off really quickly. So this is the population of dragons, and yes, there are dragons in Oxnard. You just got to look. The population of dragons in Oxnard is 1,250 with a growth rate of 2%. What will it be in 4 years? So the idea is that we're starting with some starting amount, which in this case we're saying is 1,250. And then it's growing, it's increasing. So our rate of growth there is 2%. And then the question that it asks is that says how long, or rather, I'm sorry, what will it be in 4 years? So what will the population be in 4 years? Well, so you'll notice, by the way, over here there's an exponential equation for growth. The A represents our initial amount, where something starts, times 1 plus the percentage. The percentage is the rate at which it's growing. And then the exponent is time, as far as how long it is. So there's really 3 things you got to know. Where does it start? How's it growing? And for how long? Well, so if you take a look at this particular one, and we've already kind of identified it, 1,250. Whoa. 1,250 times 1 plus, and it says 2%. If you change, by the way, if you take 2% and you want to convert that into a decimal, it's 0.02. You know, I think of money, right? There's a difference between, if I looked at a price tag that said 0.02 and 0.20, 0.02 says 2 cents, 0.20 says 20 cents. Those are two different things. So if it says 2%, that's like saying 2 pennies, right, which would be 0.02. And that would be raised to the t, which would be 4. Now I could simplify this, by the way. I could go ahead and combine. I could say 1,250 times 1.02 raised to the 4th power. Now, by the way, you might wonder, like, what's the deal with the 1? Well, what the 1 represents is where we're already at, where we already are. We're at 1,250. So we're saying take where we are plus how it's growing or how it's changing, right? So that's the idea with the 1. Now, at this point, there's nothing we can do with it further without putting it into a calculator, so let's go ahead and do that. Now, I'm not going to use my TI calculator. I'm actually going to use the calculator if you're sitting down at a computer that you would have available to you on the computer. Now, if you got a cell phone that has a scientific calculator on it, go ahead and do it from there. But just for purposes here, I'm going to show you a scientific calculator on the computer. So if you go ahead and hit the Windows, the Start button, and you pull up Programs, and you go to Accessories, you'll see the first thing listed there is a calculator. Now, by default, the calculator is going to be just a basic add, subtract, multiply, divide calculator. So if you click on View, and you'll notice the second option there says Scientific, then you can change it to a scientific calculator. Now, our rules, order of operations, are that we always do exponents first. So what you would do, you wouldn't say 1,250 times 1.02 to the 4th. You do the exponent part first. So you would do 1.02, and on this particular calculator, to do an exponent is this key right here that says x to the y, and you'll see that it says raising to the 4th power. We'll say equals, and then we'll say times 1,250. And so we get 1,353. I put the squigglies here because that means that we're kind of rounding, we're approximating. So we'll say 1,353 dragons. Right? So it's not really a word problem. I said in the beginning it's really a problem that has words in it because really they're just giving you all the numbers. You just got to plug it in and then hit that into the calculator. Alright, so go ahead and pause now and try number 9 in the middle. Alright, let's check out what you got with number 9. Number 9 in the middle should have got 493 chupacabras. Don't be afraid by the little chupacabra guy over there in the corner. He's not going to hurt you, I promise. He doesn't bite. Looks like he bites, but he won't bite you. If you got that, great. Go ahead and pause. Try number 9 on the right side. If you didn't, again, we'll kind of walk through how to do this. But again, don't just copy what I'm writing. You should have already done this, or you should have already tried to figure it out on your own. So it's no good just trying to copy what I'm doing. All right, so let's write this down. So the initial amount, so we're saying there are currently 350 chupacabras in Oxnard, and they're growing because you know those chupacabras, and they reproduce. So they reproduce at a rate of 5%. So 5%. So we'd say 1 plus 0.05, and then that is to the t, which represents time. So we're saying how much in 7 years. So to the 7th power. And again, we can simplify that. We can say 350 times 1.05 to the 7th power. And then again, from there we would put that into the calculator. I'll use my computer calculator here. So that would be, as far as the keystrokes on that, you would do 1.05 because we're doing exponents first. 1.05 raised to, that's that xy key, to the 7th power equals, and then times 350. And we'd get 492.48. Which actually we could have left that, the rounding on that, really we could have left that at 492. I rounded to 493, but technically we really could have rounded to 492. Either way, it doesn't really, I'm not so worried about the rounding on that, is that you got the right answer. Alright, and then, so pause now, turn number 9 on the right side. Alright, so for number 9 on the right side, you should have got 13,602 unicorns. And I think it's entirely possible that at one time there may have been an equestrian type animal that had some sort of horn appendage coming from their forehead as a matter of defense, protection. So I think dragons are entirely possible. Who knows? Wait, I said dragons. I meant unicorns. Dragons. Well, I think dragons are possible too. Alright, obviously it's getting late. Alright, so let's move on here and let's try number 10. How long will it be before the dragon population reaches 2,000? So we're actually kind of referring back to this first question about dragons of 1250, right? So we're kind of using the same information. So how long will it be before it reaches 2,000? So what we want to know is that if the population kept growing at this amount, right? And what this y represents, it represents the ending amount. So what we're saying is that if the population ended up at 2,000, how long would it take for that to happen? And what we're saying is that it started off at 1250, growing at 2%. So we're saying it started off with 1250. And then it's growing at 2%, right, which would be 1.02. And then we're saying, how long would that take? So, to the t power. So we're trying to get t by itself. Well, to get t by itself, what we would need to do is that we would first need to get rid of the number that's out front there. So we would actually have to divide both sides by 1250. So we're going to divide by 1250. Now let's use our calculator. When you say 2,000, oh, way too much. 2,000 divided by 1250, you get 1.6. So I would say 1.6 equals 1.02 to the t. Now what we want to try to do is we want to get t by itself. So what we would need to do is that we would need to, and again I can't do that mentally, like I don't know, 1.02 to the what power makes 1.6, who knows? Right, so that's where you got to use the calculator. Now we did do a shortcut. If you think back to number 6, right? So we ended up saying on number 6 that if you needed to use the calculator, you had to rewrite it first into a way that you can get it into the calculator. And it ended up being, I didn't mention this way back here, but there's a shortcut here, which is it ends up being log of the number divided by log of the base, right? You notice that. So we can use that shortcut here. I didn't want you to use it on number 6 because I wanted you to show the proof, but here I'm okay with it. So it ends up being that t would be log of 1.6 divided by log of 1.02. And then let me just go ahead and write that just so we know what we're referring to here. So the shortcut there is that t is equal to log of the number divided by log of the base. And what I mean by number is the number that's out here by itself, and then the base is the, well, what's at the base of the exponent. So let's go ahead and use the calculator on this. So on this particular calculator, it actually wants me to use... Oh wow, that's weird. It's probably my wife calling me to say, why aren't you coming home? Let me pause that. Alright, yeah, so that was my wife. She's like, hey, where are you? And but I'm not in trouble. I'm not in the doghouse. I told her I'm trying to do some math videos here to help my students. So that's why you're here, and that's why I'm doing it. So I think where we left off, that was kind of weird. I think where we left off was we were just needing to put this into the calculator. So let's do 1.6 and log divided by 1.02 log. And then so we get 23.73 and a bunch of numbers. So let's just round to one decimal place. So let's just round to 23.7. So let's say approximately 23.7 years. 23.7. Right. All right, so go ahead and try number 10 in the middle and number 10 on the right side. All right, so let's see what you got with number 10 in the middle. So you got 14.2 years. How we got that is that we wanted in to see if we ended up with 700 chupacabras when we only started with 350, and then, you know, how long would that take? So 700 times 1.05 to the t, which would be time. And then we said the first thing that you got to do is you got to get rid of the number that's out front. So we would divide by 350, which would be 2. So we get 2 equals 1.05 to the t. And then we said t is equal to log of the number divided by log of the base, 1.05. So let's hit that in the calculator, see what we come up with. So we end up with 2 log divided by 1.05 log equals 14.2. And if you wanted to see what you got for number 10 on the right side, it should have come up with 8.5. Alright, well, so that concludes this video. Thanks for hanging in there. I know you wish it could have gone longer, but there's only 10 questions, so we've got to stop here. But hopefully you feel better about the logs. For a lot of you didn't do very well the first time on this, but that's okay. It's a new idea. You've never seen this stuff before. But so here we are. I think we're in a better position. So we'll go ahead and leave it here, and I think you're ready to redo the test. All right. Well, thanks for hanging in there with me.